Hey guys, now we're in section 9.4, which is a proof technique called mathematical induction. So the way mathematical induction works is you show that a statement is true for the natural number 1. And then the next thing you show is that if it is true for k, then it is implied that it is true for k plus 1. This sets forth a domino effect because we've shown it's true for 1. And then the second condition says, well, then if it's true for 1, it's true for 2. And if it's true for 2, then it's true for 3, and so on and so forth. So in order to use this technique, you must show both conditions, okay? And once you've shown both, then you're done. So let's try the first example. This statement says that 1 times 2 plus 2 times 3 plus 3 times 4 times ... plus n times n plus 1 equals 1/3 times n plus 1 times n plus 2. So the first step is to just show that it's true for n equals 1. So this is condition 1. So we're going to let n equal to 1. And then we're going to take a look at both sides of the equation. So then, I'm looking right here, n times n plus 1 is 1 times 1 plus 1, which is 2. Now we're going to look at the second side. And now I'm looking over here, 1/3 times 1 times 1 plus 1 times 1 plus 2 equals, okay, let's simplify this a little bit more. So I have 1/3 times 2 times 3. Okay, well, 1/3 times 3 is 1 times 2, so it's also 2. So they are the same. So this is true for condition 1, so we're good there. Now we're going to go to condition 2. Okay, so now we assume that the statement is true for k. So we will write that out. Assume 1 times 2 plus 2 times 3 plus 3 times 4 plus ... plus k times k plus 1 is equal to 1/3 times k plus 1 times k plus 2. Now, what we want to do is show that if this is true, then it is implied that it's also true for the next case, which would be the k plus 1 case. So how do we show that? Well, I would write a note off to the side or maybe down below to help us to organize our thoughts of what we want to do. So let's do that. This is not part of the proof. This is just me organizing my thoughts. I'm going to say we want... And what I want is the statement to be true for the next case, which would be just adding one more. So instead of k plus 1. So that would be 1 times 2 plus 2 times 3 plus ... plus k times k plus 1. That's what I have above. But now I'm looking at the next case, which would be k plus 1 times k plus 1 plus 1, so plus 2. We want to show that that is equal to 1/3 times, now I'm replacing k with k plus 1, so k plus 1 times k plus 1 plus 1, so k plus 2, times k plus 1 plus 2, so k plus 3. So we want to show that this is true and that it follows from the assumption. So we do that by kind of expanding on this idea that we already have here. Then, okay, now I'm going to start with the k plus 1 case. So it would be 1 times 2 plus 2 times 3 plus ... plus k times k plus 1 plus, then the next one would be k plus 1 times k plus 2 is equal to, and what we can do is replace this portion with this, right? We've assumed that they're equal, so we will make a replacement, and that is by our assumption. So I'll replace this first part that I underlined with 1/3, oops, I don't need the parentheses, 1/3 k times k plus 1 times k plus 2 plus this next term that I kind of added on, k plus 1 times k plus 2, and I'll put a note, by our assumption. Okay. Now looking at this is not what I want. What I want is down here. Okay, so the main difference between what I have and what I want is that what I have currently has two terms, and what I want is just one giant product. So it looks like if I factor, I might be able to achieve what I'm looking for. I'm seeing common factors here, k plus 1, k plus 2, k plus 1, k plus 2. I think I'll factor those out and see what happens. Sometimes you have to just try stuff. So I have k plus 1 times k plus 2, and what's left is 1/3 k plus, nothing left there but a factor of 1. I'm going to put factoring. Okay, so later if you're looking at this, you'll know what we did. Pretty close. This one has a factor of 1/3 in the front, so maybe if I factor out the 1/3 from that last portion in brackets, I will have what I want. So I'm factoring out a 1/3 from the last sort of binomial factor. And when I factor out 1/3, this becomes just a k. And this, 1 divided by 1/3, is a 3. And if you look there, you'll see we have exactly what we wanted. So that's great. So this means that the statement is true. So I'll put kind of a little summary. Both conditions hold. So the statement is true. By, and then we have a shortcut of writing this, the PMI, which stands for Principle of Mathematical Induction. And when you finish a proof, you would normally draw some sort of square or some sort of symbol. Square is sort of the accepted one. So I know this is probably new for a lot of you writing proofs, so I'm going to do a couple more just to hopefully get the steps down. The basic structure will always be the same. Condition 1, show that it's true when n is 1. Condition true, assume that it's true for k, and show that by assuming it's true for k, then it's also true for k plus 1. In other words, that the k case implies the k plus 1 case, and that triggers the domino effect, which is how induction works. Okay, so let's try the next one. 1 plus 3 plus 3 squared plus ... plus 3 to the n minus 1 equals 1/2 times 3 to the n minus 1. Okay, so we're going to show that this is true when n is 1. This is condition 1. Let n equal 1. Then 3 to the 1 minus 1 equals 3 to the 0, which equals 1. And so that's the left-hand side. Now we'll go to the right-hand side. 1/2 times 3 to the 1 minus 1 equals 1/2 times 3 minus 1 equals 1/2 times 2, which is also 1. So this is the same as this, so it's true when n equals 1. So we've shown condition 1 is true. Now we go to condition 2. We assume it's true for k. Oops, 2. Assume 1 plus 3 plus 3 squared plus ... plus 3 to the k minus 1 equals 1/2 times 3 to the k minus 1. So what we want to do is show that if this is true, then it follows that it's also true for k plus 1. So I think it is helpful to write off to the side of what we're looking for. This is not part of the proof. This is just our thoughts. We want, I'm going to replace n with k plus 1. 1 plus 3 plus 3 squared plus ... plus 3 to the k minus 1 plus 3 to the, okay, so k plus 1 minus 1 would just be k. So show that's equal to 1/2 times 3 to the k plus 1 minus 1. So we want to show this, that this follows from it being true for k. So we go ahead and add on to what we know. Then, if I take this left-hand side, 1 plus 3 plus 3 squared plus ... plus 3 to the k minus 1 plus, and then add on the next term, 3 to the k, what we can do here is make a replacement. Okay, we already know this is what we have here. So I'm going to make a replacement. I'm going to replace it with this 1/2 times 3 to the k minus 1. Why can I do that? Well, I assumed that those things were equal. So if they're equal, you can just replace them with each other. So this is 1/2 times 3 to the k minus 1 plus 3 to the k. So keeping in mind what I want is over here. I want to turn what I have here into that. You can trust they are equal. You just have to be able to show it algebraically. So how can I do that? Well, first maybe get rid of the parentheses. They're kind of keeping me from combining things together. So let's do that. Let's distribute the 1/2. 3 to the k over 2 minus 1/2 plus 3 to the k. Okay, maybe I want to combine the 3 to the k over 2 plus 3 to the k. So I'm going to need a common denominator. So let's go ahead and get a common denominator by doing 2 over 2. Okay, so now I can add those together. So I have, well, I'm going to put a note over here just so we can understand what's going on. I have 3 to the k over 2 plus 2 times 3 to the k over 2. So if I have 3 to the k plus 2 3 to the k's, what do I have? I have 3 of them. Okay, so notice that in that first fraction, 3 times 3 to the k over 2, the bases are the same, so I can add the exponents. I didn't write it, but 3 is 3 to the first power. So add the exponents together, k plus 1. There we go. That's just using the laws of exponents. So it looks like I'm super close. The last step, I believe, will just be to factor out 1/2. And I have 3 to the k plus 1 power minus 1, which is exactly what I wanted, right, over here in my box. So I'll write a little summary. Both conditions hold. So the statement is true. By the principle of mathematical induction. We're going to try one more that is a little bit different. This one you'll see it's a sentence, but you can still use induction to prove this. N cubed plus 2n is divisible by 3. First of all, that's pretty amazing that that's true for any natural number n, but we're going to show it. So first we show it's true for n equals 1. So here's condition 1. Let n equal 1. Then 1 cubed plus 2 times 1 equals 1 plus 2 equals 3, which is divisible by 3. So condition 1 holds. Now we're going to assume that this statement is true for some natural number k. Condition 2. Assume k cubed plus 2k is divisible by 3. So we want a way of writing this out as an equation as opposed to a sentence. So we can do that by writing out this equation. Then k cubed plus 2k equals, so I want to express a number that's divisible by 3. Well, any number that's divisible by 3 has a factor of 3 and can be written as 3 times something. So I'm going to just say 3m. So 3m is just representing a number that is divisible by 3. So what is the m? Well, m is just some integer. Okay, so we're assuming that's true. Now I want to take a look at the k plus 1 case. Okay, so let's go ahead and just replace k with k plus 1. See what happens. See if we can get any algebra. K plus 1 cubed plus 2 times k plus 1 equals. So I'm going to simplify this in the hopes that I get this at some point, because this I know I can replace. Okay, so let's see. K plus 1 cubed, I hate to be mysterious, but this is k cubed plus 3k squared plus 3k plus 1. How do I know that? Well, that is a shortcut you will learn in the next section. I use the binomial theorem. So I know the cube binomial expansion. You will learn it in section 9.5. Now I'm going to distribute the 2. Okay, so what I'm looking for is, I'm trying to get k cubed plus 2k because I know I can replace that. I'm seeing it, so I'm going to reorder the terms a little bit. So I have the k cubed plus 2k that I wanted, plus I have some other stuff. I have 3k squared plus 3k plus, I also have 1 plus 2. I can combine those as a 3. So this, I am assuming, is equal to 3m. So I'm going to make that replacement. Plus, and I'm going to factor out a 3 here. Oops, I'm factoring out the 3. So that first part, the replacing k cubed plus 2k with 3m was by our assumption. Why am I doing that? Well, I want to show this entire thing is divisible by 3. And I'm seeing that both terms I have here contain factors of 3. So if I factor those out, I get 3 times m plus k squared plus k plus 1. Okay, and that is divisible by 3. How do I know that? Because there's a factor of 3. It's factored out for us. So I've shown that if it's true for the k case, in other words, if k cubed plus 2k is divisible by 3, then it follows that k plus 1 cubed plus 2 times k plus 1 is also divisible by 3. So I've shown both conditions. So we can write a little conclusion, which I will be looking for on your test. Both conditions hold, so the statement is true by the PMI. And we have proved it.